Good. Archiving started.
So we're good to go?
Okay, we're good to go.
All right. Well, first off, I want to say thanks to everybody for making the trek in, especially all of my students. No, more importantly, the parents in the crowd. Awesome to have supporting faces here for this. But I thought today would be a great opportunity to give the two undergraduates who are so fortunate for me, and hopefully for them too, dedicated a vast majority of their time to doing something productive, namely real research here at Georgia Perimeter. I started this research many moons ago at Georgia State, continued it at Virginia Tech, and I've picked it up here, and luckily had great helpers who were willing to lend a hand on the cheap. So, what am I talking about today? Well, we're going to be talking about quasars, namely a specific type of quasars. I've studied AGN. I'm going to use these terms interchangeably. AGN stands for active galactic nuclei. That is completely synonymous with the word quasar. We're going to be talking about a very specific type of quasar, ones that have something called BALs, broad absorption lines, and even more specific, ones that show signatures due to iron, low ionization, English is a good language, low ionization iron lines. The picture you see on the screen is roughly what we think these objects look like. Yeah, will that kill your camera?
Oh, no. I hope not. Well, if not, I mean, we have the images, so that's fine.
Sure.
Yeah.
So you see the purplish kind of filamentary structure here. This is not what I studied. I'm going to say that like 3 times. You'll have to bear with me. That's not really what I studied. This is what we think what I study looks like. The reason we don't know what I study looks like is because it's too friggin' far away. So it's really small. This is actually a supernova remnant, but we think the outflows that I study that come from quasars look much like this. Cute. So I figure since I have a very broad audience here, not everybody in this crowd has taken, Astrophysics 4000, it wouldn't hurt to give a little bit of background. Let me introduce you to astronomy. This is a good friend of mine. You guys were supposed to see it at Hard Labor Creek Observatory the other night. That's Saturn. Probably one of the coolest things to look at through a telescope ever. This is our sun, and that is a star. I don't study these at all. What I study is vastly bigger than these. Saturn is many times the size of the Earth. Sun is even bigger than that, many times bigger than Saturn. And there are many stars, I believe that's supposed to be Betelgeuse, which is even bigger than the Sun by a lot, like the size of Mars's orbit or bigger. That's how big that star is. And they all pale in comparison to what I study. So, we need a little bit of perspective here in order to figure out what it is I'm talking about. This is what we think the Milky Way looks like, a barred spiral galaxy, something on the order of 200 billion stars, and we get one of those little guys. And we think, distance-wise, we are in the red box there, kind of halfway to the edge. Now, the middle of the Milky Way is a supermassive black hole. Supermassive meaning it has a mass of order millions of suns worth of mass dumped into one black hole.
All right. When you say we, are you referring to our solar system or Earth?
Where we are? Right. We're this little arrow point.
Are you referring to our solar system?
Solar system. And the supermassive black hole is here in the very middle. And on this size scale, if you take the middle pixel here, the dead center, you have to keep getting smaller. It's that small relative to the size of the Milky Way. We're kind of halfway out. This is about 8 kiloparsecs from here. 8,000 parsecs, which translates to something like 24,000 light years from the center of the Milky Way. And it'll be about another 8 to 10 to the edge of the galaxy. These are important things to remember where we are, because the sizes of the things I'm going to talk about, I'm going to put them in scale compared to our Milky Way. Okay? So this is Milky Way. Again, not what I studied. Next slide. So, I forget, you don't get animations with this. Ah, crap. So behind this is a beautiful barred spiral galaxy. It is not the Milky Way. I was going to go and point out that we've got the supermassive black hole. It is what we call a quiescent black hole, meaning it's a black hole that's not doing anything interesting. Again, not what I studied. What I studied, and again, this is not going to come out right. It's a series of pictures. I forgot that you don't. Okay. Next slide. What I studied looks something, I believe, like this. So when you take the big picture and you zoom way in to that middle pixel and you keep getting smaller, we eventually come to some galaxies that have a black hole that's currently active. And by active, I mean actively feeding, right? You always hear sharks are the apex predator. No, these don't. These eat everything. So something happens. I'm not so concerned about what happens to trigger this, but gas and dust get funneled down to the middle of the galaxy, creates an accretion disk, meaning I'm feeding stuff into the black hole across the event horizon. That's the point of last return. And as I'm feeding it, it gets really hot and really bright. So bright, it outshines the rest of the host galaxy. The quasar is the very middle pixel. The rest of the galaxy completely invisible to us because it's being outshined by that. 200 billion stars versus one accretion disk. Much brighter. So bright that it completely dwarfs the rest of the host galaxy. And this is all happening in that middle pixel. That is a quasar. Black hole accretion disk. Bottom line. Next slide, please. Still not really what I studied, but much closer now. So this is another artist's conception. Clearly these are all artist conceptions because they're too small and too far away to really get a good picture of. So most everything I do is artist conception. This is what we think an accretion disk looks like, with my black hole down in the middle. This is one depiction of it. But the important thing is this shows this kind of whitish stuff being blown off, right? Well, it turns out black holes are messy eaters. As you're feeding them, they're like 4-year-olds. They get stuff all over the place when they're eating. It's a mess. You need a bib, right? I studied the stuff that they dribble and drool all over the place. Yes, I actually said that. So this is outflowing gas as it's funneling in. That gets really hot and bright. So bright and so hot that it pushes on the gas that's coming in and actually pushes it back out at very high speed. Thousands of kilometers per second in some cases. That's the stuff I study. I study the winds. So I'm going to refer to quasar winds, and that's exactly what I'm referring to. Most of the time, I don't think they're this close. This all happens on a scale of a couple light minutes across. What I study is at much larger distances, and I'll explain why in a second. Next slide, please. So how do I do my study? Well, I need to take a spectrum. So this is a spectrum of a random quasar that I decided to take. And you'll notice a few things about it. I have a nice slope going upwards, nice roughly constant line increasing as I go towards shorter wavelengths. So a spectrum, I'm taking like you've all seen a prism before and it spreads out a rainbow. That's all we've done here. We put the light through something akin to a prism, spread out the light, and then took a picture of it, and then read it digitally. So this is the amount of light per wavelength, like Roy G. Biv. Cool? So we have the increasing slope. We have emission lines on top of them. The funny part is, these emission lines, this is magnesium 2. This is going to be very important in a few minutes when Brandon talks. This is magnesium 2. This is carbon 4. So look at these rest wavelengths. That's 1,500 or 1,500 angstroms, 3,000 angstroms. This is far shortward of human visibility, aka the ultraviolet. We're kind of sandwiched right in there between X-ray and visible. So this is actually emitted originally in the ultraviolet. We, however, see it in the visible. Cosmological redshift moves the UV spectrum that was put out by the quasar into our visible spectrum, and we take a picture. It's a very handy way to look at the ultraviolet data from any kind of quasar. All right, so this is a healthy one. Let's look at a not so healthy one, or one example. This is much more messy, isn't it? We've got a little bit of continuum here. Then I have this big, giant drop. Here are my emission lines. This is a mess. We don't have to worry about this so much. So we just kind of chop this off. We'll go right here. And we see that we have very large absorption lines, very broad absorption lines. And it's these absorption lines that I specifically study. They are also, if this is carbon-4, they are to the blue of carbon-4. They're to the blue because it's Doppler shifted. Blue shift means it's coming towards me, so that stuff is moving towards me at the quasar, really, really far away. And it's in between me and the quasar, thus it creates an absorption line that is blue shifted. Now we refer to these as BALs, B-A-L. This is carbon-4. We're going to be referring to magnesium-2 in a second. Magnesium-2 is a lower ionization species, technical jargon for anybody who likes that. And that's why we call it low-BAL. So this is a high BAL, magnesium is a low BAL. Okay, next please. Now, out of curiosity, why should we care? Well, the text in the background you can clearly read. That these outflowing gases, they can push on stuff a lot. There's a lot of material, a lot of energy, and those are needed for something called feedback. So quasars send all this gas back out, and so let's say there's a star-forming region in the vicinity of my quasar. This gas comes sweeping by, and in order to make stars, I need gas and dust. So if I come and I sweep up all of the gas and dust making stars, no more star formation. It's done. I've taken away the supply. I've cut off the source. So that's one thing it's important for. It's also important, this is the Millennium simulation. This was done at the new Millennium, 2000. Carlos Frank was part of that party. And basically they put the universe in a box and said, go. And so they let time roll on, they let all of the hydrogen interact, and this is the picture they came up with, and it looks really close to our universe. The galaxies that are made in the box are too big. There's a very specific ratio of how much mass the black hole has versus the mass of the galaxy. This doesn't match that at all. The galaxies are too big, the black holes are too big, so we need some kind of mechanism to prevent the black holes from growing. If I'm feeding gas in, the black holes make it bigger. What's the easy way to get rid of the stuff I'm feeding it? You blow it back out with wind. So that's why this is important, and this is a very important problem in solving our current picture of cosmology, of solving the Big Bang Theory, making sure that this all works. Okay, next slide, please. So what do we think we know about these outflows? There have been a lot of studies, including a couple by this brilliant author, Dunn et al. I've done a lot of work in this area. Frequency, how often they show up, how often do I see BALs, because it doesn't happen all the time. It's something like 20% for carbon. So if I look at a quasar, I got a kind of 1 in 5 chance that I'm going to see a BAL. If I look at the velocities, I can get that right from the spectrum, thousands of kilometers per second. Distances is a little trickier. I'm simply looking at a spectrum. So I have to kind of go around my elbow to get to my backside to get to it. And so we need something that can give me the density of the gas. And that's where the iron comes in. Iron low-BALs are the only way to get distances currently. Well, one of the distances. This is the easiest way to do it. We can also talk about the size, this direction. That omega up there, that's the size of the outflow. The distance is how far away from the accretion disk in the black hole. The other pictures that I'm going to leave to the modelers because I'm not nearly qualified to handle this, or where does it come from? Where exactly does the outflow start? Does it start from the accretion disk? Does it start from other areas? Does it start as it's fallen? I don't know, and I'll let somebody else deal with that. I'm an observer. Okay, so the distance scale, let's look at the next slide. Kiloparsecs. Right? The accretion disk black hole are in the center pixel down here. These outflows are out at, the last one I measured was 5 kiloparsecs. Over half the way from the middle of the Milky Way to us. That's how big these things are. And they sweep up huge swaths of the galaxy. Okay, next one. So this is an iron low-val one. This is actually aluminum. That's iron 2. So we use these to get the density and the distances. I'm going to skip ahead. I need to give you guys enough time to go. Not so healthy AGN next, please. This is what it looks like for an iron valve. Here's my normal healthy spectrum. Here's the one that needs medical attention. They're all like this. Now the question is how many of them and why? And the answer is reddening, which I'll let Kristen talk about in a second. But it's an important piece of the puzzle as to where the distances are, because ultimately it depends on whether the reddening that's causing this occurs before, between the black hole and the outflow, or after the outflow. If it occurs before, it changes our distance determination. Meaning I could say it's 5 kiloparsecs, but if the reddening is really outside of that range, then it's at 20 kiloparsecs. I've got a factor of about 4, so I need to know where the dust is. It's a very important piece of the puzzle. Okay, next one, please. So in order to understand this full picture, we need to put together I call this the exploding bagel. It looks like an exploding bagel. So we have our black hole accretion disk. We've got these things that generate broad lines, not so important. These are part of what make those emission features on the spectrum. We've got a obscuring torus, which is kind of important because it's all about view. If I'm looking this way, I can't see any of that stuff down here. All I can see is this gas out here, which is narrow line in this very peaky line. If I'm looking straight down the hole of the donut, then I'm going to see the broad line, the accretion disk, the narrow line. I see everything. Now, there's a very unique picture that if I'm looking kind of along the edge of the torus is made out of dust, which can provide that reddening, then I can obscure part of this, give myself the reddening, and I've got a source for the dust that's very close to the quasar. The key to remember is that if that's my case, if this is what's reddening that continuum and making it slope down, the stuff making the narrow lines is out too far to obscure. So the narrow lines should not show any effects due to dust. I'm seeing them cleanly. So that's the important takeaway from this. Okay, next one, please. Next one. Keep moving a little faster. So here's my picture. That's my outflow, the green arc. And I have a couple of different possibilities of where the dust could be. If I'm looking this way, then I see the edge of the torus, so I see the reddening, which reddens the background, which is the accretion disk. But it doesn't redden the narrow line. The dust could be between my outflow, out in the host galaxy. I mean, 5 kiloparsecs is a lot of space to cover. There could be a lot of dust there. So if I put it in between the outflow and the source, now I'm going to redden the narrow line and the background. If I'm out there, put the dust on the other side of the outflow, now I'm reddening the outflow, the narrow lines, and the center parts. So that's my question. So in order to start working on this, I need somebody to go through a bunch of quasars. So I turn it over to Brandon Wasik.
What is the composition of the dust?
The dust is primarily polyaromatic hydrocarbons, PAHs. Yes.
And
It's much like wildfire smoke.
No hydrogen here?
There is hydrogen mixed in, but it's mostly in molecular form. So it's molecular hydrogen. The gas to dust ratio, if I remember, is about 0.6, I think. I have to double check that, but somewhere in that order.
Jay, one more thing. I forgot to make a sign-up sheet or a sign-in sheet.
Okay.
So maybe if someone has a course.
Thank you, Brooke.
Awesome.
All right, so this is Brandon. I turned Brandon loose last summer on a search through the Slim Digital Sky Survey, and I'll let him tell you all about it.
All right, so I'm Brandon Walkley, by the way. And today I'll be talking about the research I've been doing with Dr. Dunn. This here is the Slim Digital Sky Survey. This is the telescope that they use. It's a 2.5 meter aperture telescope. It's located in Apache Point, New Mexico. And the way that they get a spectra is by, they have these huge metal plates, and using fiber optic cable, they just punch a hole where the galaxy is, and they're able to catch the light from it and everything, so that the spectra is not, interrupted by other light. So this is the instrument we use. It's pretty big. And in order to access this information, we go to the SDSS website. This in particular is data release 7. For reference, data release 1 and SDSS both started in 2000, and they've had up to DR9, I believe, yeah. And we're using 7, which was released in 2008, and this is the page where we specify the magnitude, the redshift, and and the fact that we're looking for quasars. We're not looking for stars. We're not looking for other things. So what is magnitude? Our magnitude scale is backwards. I'm sure y'all heard that. Where a high number means that the light is incredibly faint, and a low number means that it's high. And the magnitude that we're looking for is less than 19. So if we go into 19, then we get a spectrum that is too noisy to make out, and this is what it looks like. You can tell that it's a huge mess compared to the ones that Dr. Dunn showed you. And really the only thing that you can see is this peak right here, which is magnesium-2 emission. And these lines right here are the uncertainties, and as it gets noisier, we have no idea what we're looking at, pretty much. Next. Our sample size consists of 8,510 quasars. I had to go through each one individually and determine how many had magnesium-2 and iron-2 broad absorption lines, or I'll refer to them as FeLoBALs from now on. And we're looking at, we start at Z equals 0.45. And this is the cosmological redshift. This is how fast the galaxy is moving away from our point of view. And for reference, that's 135 kilometers a second. No, 135,000 kilometers a second. It's 0.45, the speed of light. Yeah, and that occurs at 2,800 angstrom. And as you can see, at the top, it's the UV ultraviolet range, but we actually see it in the visible range because it's been redshifted. It's just like Doppler effect, where as it's moving away from you, the wavelength becomes longer. You've all experienced that with a fire truck. And what I've been looking for in particular is this guy right here. This peak right here is magnesium-2 emission. So I'm looking for the absorption, stuff that's loose shifted to the left of it. That means that the outflow of this quasar coming towards us. And we have a very fine line between broad and narrow. Next. Because whenever I started research, I said, Dr. Dunn, I have 150 valves. He's like, no, you don't, because that's impossible. And that was because I kept showing him that I had narrow absorption lines. And we draw the line between broad and narrow as 25 angstrom. So more than 25 broad, less than 25 angstrom is narrow. And we just throw these out. These aren't valves, they're now. Next. we found a total of 70 magnesium 2-valves. This is about 0.82% of our total sample size, so that's how often, that's the frequency. Our next step is to find iron 2 broad absorption lines, because iron 2 only shows up with magnesium 2. So you find all the magnesium 2, now I just look at those 70 and find iron 2. That's exactly what I do. And the reason we look for iron 2 is because these are the types of quasars that give us distance. We know that they are part of the host galaxy and not just anywhere else. Next. This is an example of an iron 2-valve. As you can see, the continuum should be continuing up like that, but this huge iron valve is bringing it down, and these occur at 2,600 angstroms, and there's a few other ones, but that's our strongest point. That's where we check first. Next. But it's not always so clear whenever we have an iron valve. So we have this process I like to call IDing, which is I took all 70 magnesium FeLoBALs and used a program in IDL, which is the program that's shown review, and we anchored a point where the magnesium 2-valve is, and then the program tells us where the iron 2-valve should be. And as you can see, I anchored it somewhere over here, and it told me where everything should be, and these two right here line up perfectly with the iron 2. So this is an iron 2-valve. Next. We found 15 FeLoBALs out of the 70 magnesium, but out of our total sample size, this is about 0.176%. And our next step is to now look through those 15 and find ones that have strong oxygen 2 narrow emission. And that's but and the reason for this is because this helps us with our regimen, which Kristen will get to later. Next. This is, as you can tell, this is an example of magnesium and iron valve. This is iron, but this right here at 3740 angstrom, this big peaky guy is O2, oxygen 2, and that's what we look for in this, step. Next. We found that 7 objects have strong narrow emission for oxygen 2, which is about 53%. And our next step is to find H beta and H gamma narrow emission, which, and this is the reason why we stop at Z equals 0.9, because if we go past like the Z equals 1, then we're no longer able to see H beta, so we don't use it. So we stop at 0.9 because that's where it's no longer visible to us anymore. Next. This is an example of the process I like to call line fitting, where this is our H beta, and we have a broad line which has velocity, and because how broad it is determines how fast and on top of the broad emission, it's kind of hard to see, but there's a narrow emission behind the blue line. It's hard to see, but
I have another one in a minute. You'll see another example of this.
And that's what we look for. That's our next step, actually, for. Next. And of those 15 FeLoBALs, we found that only 4 have H beta and H gamma emission, which makes these incredibly rare objects in the universe. And that's it.
All right, so we now have our sample of objects. We've got the ones that have narrow emission, which I'm going to measure. But in order to have a basis of comparison, I need to look at the reddening of the quasar. Remember, we had the one that was moving upward toward shorter wavelengths, and it turned down the unhealthy spectrum. I need to know how unhealthy it is. And so we have a certain thing that describes that, which Kristen's going to talk about. You got it?
so what I'm looking for are the galactic and extragalactic extinction values for these quasars. We can go to the next one. There are a few things you guys may be wondering, what is extinction? And as Dr. Dunn and Brandon mentioned, it is the reddening of the quasar. And basically, it's the light being attenuated by the dust. I'm sure most of you have seen this. You go out at night and you look at the stars and they twinkle. And this is basically the same principle where the light is going through dust and it's being scattered. The light that gets scattered is more blue because it's at a shorter wavelength, and so the shorter wavelength gets scattered more than the longer red wavelength. Also, EV minus C stands for extinction, and it's blue minus visible, visible being what we see. Yeah, yellow. And so here's basically what I was talking about with the attenuation. As you can see, the red light isn't really affected by the dust, whereas the blue light gets scattered all over the space. And so what we look for to kind of anchor our quasar are J, H, and K magnitudes. These are in the infrared
For us.
For us, yeah. Since they travel so far, they're in the infrared for us, but they're actually emitted in the visible range for the quasar. Okay, and so just to kind of give you an idea of what we're looking through is, you can see we're right here, the sun's location. Yeah, I can't reach that high.
Right up here.
Yeah. And so when we're looking out at something, there's different amounts of dust that we look through. And so, yeah, like there's a lot more. And not only is there dust from our galaxy, but there's also dust in the host galaxy we're looking at. So for example, if we were looking at something through here, we'd have to account for all the dust through the Milky Way and whatever amount of dust we're looking at in there. And so we use this website and we type in the coordinates of the quasar we're looking at just to see how much dust in the Milky Way we're looking through. Okay, we can move. Okay, so here is an example of a quasar. This is basically what Brandon would give me from his process. And I would use these, and you can see it's got iron in it because it goes down towards the end right there. And so in this is basically what I would do with the curve fitting. This red is an average of the quasars. So if you were to take any quasar, it should look like that. And the black is the quasars that we typically look at, and they're heavily affected by the iron. And the green is what I've accounted for in the reddening between the Milky Way and the host galaxy. And then here, his points are the J, H, and then the K magnitudes out here. So you can't really see it as well in this picture, but they kind of line up towards the end and they don't move at all. And then the yellow line at the bottom is from the small Magellanic Cloud. Okay, and so here is an example of a quasar that I looked at that isn't really reddened very much. And you may be able to tell because it lines up fairly well with the average curve for quasars. And then you can see better here the J and K magnitudes. They really don't move at all. And so this one has a Z, or cosmological redshift, of about 0.01, so it's very minuscule.
Oh,
Oh, right, EV minus 3.
what was the EV minus the last one? Do you remember? I would guess that was about 0.2. So.
Well, in the next one, this one had an EV minus C of about 0.1. So you can see the difference. It moves up a lot more than the last one. And the original one doesn't exactly match up very well with the average. And move to the next slide. The red curve, the average curve, comes from the first Bright Quasar survey. In this survey, they found 219 random quasars, and they used these to
Make
an average.
which is what you compared to.
Yeah. And so in that sample, the Z ranges where we find the Z of greater than 0.1. I keep doing this. The EV minus V value, I'm sorry, the reddening value is greater than 0.1. It's only about 1 in a sample of 219 quasars. And then we look at the FeLoBAL sample, which are the magnesium FeLoBAls, and we find it's 20, so 14 of our sample size of 70 will have the EV minus V value is greater than 0.1. And then if you go to the iron sample, it's 28 of the 70 have an EV minus V value of greater. So the more you go with the iron, the higher the EV minus V value will be.
Good. So what that means is, I'll take over again, so we can switch back to my slide. So what that means is that fundamentally there is something different about FeLoBALs compared to normal quasars. The question is where is that reddening? Where is the dust in the quasar? Now, in order to make iron FeLoBALs, you really need to attenuate the light a substantial amount before it gets to the gas, or you have to put it at a very large distance. One of the two, or both. And so the torus makes an ideal way of reddening that light, giving you a really specialized sight line. So we can go back to my previous one.
Okay. Yeah.
That one. So the odds of me seeing right along that slim sight line are pretty slim. Slim sight line, you like that? The odds are pretty slim of me getting this very specialized sight line. So a lot of people attribute it to the fact that I've got this very special scenario. And it's a scenario that would produce reddening in my line of sight. So it's a really great way of saying, yeah, we've solved it. It's clearly inside. I wanted to test this. There's another school of thinking that in order to make a quasar, you have to have some kind of galaxy merger. Two galaxies, they come together, they spiral in, they tear each other apart, one cannibalizes the other. When that happens, it's a terribly violent process. You disturb the gas, which is an ideal way to make that gas funnel down and feed the black hole. While you're doing that, there's tons of dust and gas everywhere, out in the host galaxy. So it's possible that FeLoBALs are just an evolutionary state immediately following a merger before everything settles back down. And so a lot of evidence these days is pointing towards that scenario, and so I wanted to test whether the torus works or not. And the best way to do that is to look at the narrow lines that Brandon found and compare the reddening of the narrow line to the extinction of the background. This is clearly extincted, and we just said for FeLoBALs, 40% of the time, it has an EV minus V of greater than 0.1, which is 40 times more than a normal quasar sample. That's statistically significant by a lot, right? So, since the reddening is there, I can measure the amount of reddening here, and I can measure the amount of reddening here using the H beta and H gamma. So if we can go to the next slide. Here are the 4 quasars that Brandon found. Actually, there's 5. I had one a priori that I put into the sample. I have friends in high places who hooked me up. This is actually a Magellan spectrum, 8-meter class telescope in Arizona. So this is a much higher signal to noise. It turns out it's not terribly useful. My 2 darling spectra are up here. 0802, that's the phone number on this one. 0802 plus 5513 and 1344 plus 3317. Remember that, there will be a quiz. So clearly we've got strong emission here, right? Here's the O2 line that Brandon found. H beta is right here, and H gamma is kind of right here. So we've got decent H betas that I can measure, and he was talking about fitting the line. He was doing that to detect the line. I actually want to measure the ratio between them because they have an intrinsic value that they're supposed to match. One is supposed to be 5 times bigger than the other one, for example. So if they're not 5 times comparatively, then clearly there's an reddening, which is extincted the gamma. So we go to the next one. So here's one of my fitting processes. This is zooming in really close, and I've normalized the data so it should all be sitting on 0 unless it's an emission feature. And what I've done is you see the red on top of the black. There are other emission lines that are completely independent of these hydrogen lines, namely O3, oxygen twice ionized, at 5007 angstroms. That line is a very strong, narrow emission line, and it is only narrow. It has no broad component. So what I did is I took a copy of that, moved it over to H beta, scaled it to match the size of it, and then scaled another one to H gamma. And you can see the fit for this is pretty dang good. This one gets a little wonky over here, but there's a lot of noise on the edges. So this is a pretty dang good fit. And the EV minus V you get in order to make this happen, because it's not the intrinsically proper ratio, is about the same as the EV minus V of the background, of how much it's turned down. That seems awful coincidental to happen and not come from the same EV minus V source. The same reddening source doesn't have to, but the odds are in my favor. The same source is going to redden this as much as it did the continuum. More,
Wait a minute, I think hang on, here we go.
Okay, I thought I threw one more in there. But the bottom line is that from our sample of 4 or so objects, I mean, it's not a lot of objects to play with, but we're taking what we're given. It looks like in each of those cases, all 4 cases, the EV minus V value of the continuum is consistent with the narrow line. That's a pretty, strong case that this stuff has to be outside of the torus because the narrow lines are all reddened and they're reddened about the same amount as the background. So I think that about does it for us. We'll take questions now. Come on up, guys. Come on. You're part of this too. Yes, sir.
Thank you. The instrument that you guys are using, on it's in Alga. It's S-bound platform.
Yes, it is.
And that means the days that not covered,
Yeah.
like anything.
Right.
I wonder, have you tried with an access to use the space-bound telescope, the Hubble telescope?
So the question is we're using the Sloan Digital Sky Survey telescope, which is a ground-based telescope. He's wondering if we could access space-based telescopes. So there's a couple things here. One, I could propose to put in an HST proposal. I've done that before. Your odds of getting it are pretty, like 1 to 20 odds of getting an HST proposal accepted. I'd love to, but for what we want to do, we only need 1 observation. So I didn't put in time with Sloan to get them to look at these. Sloan is an archived database. Basically, he was talking about you get the metal plates with fibers. They'll take a picture of the sky, put their fiber feeds in there, do 600 objects at one time, move, do another 600 objects, move, do another 600, and they just cover as much of the sky as they possibly can. And so all I need is 1 spectrum. I would love to go back and say, okay, well, this FeLoBAL had this EB minus B. Let's do a subsequent observation, see if it looks the same, see if everything is jive over time. Because there is evidence that some LoBALs, or some BALs in general, change. The good news kind of here is quasars don't change on very short time scales. Their fluxes and all of their properties tend to stay solid for decades or so. So even if I took a subsequent observation, the odds of me getting something different would be pretty slim, which is why I don't think I could get a proposal through HFT for that. But okay. Does that answer your question?
Yeah,
Awesome. Anybody else?
What happens after the quasar dies?
What happens after the quasar dies? So the quasars, that's the question. What happens after a quasar dies? So the quasar is currently accreting matter, and that's what's making a quasar. That's what's giving the luminosity, the brightness. So over time, I'm going to keep funneling gas into there, but I'm going to run out of fuel eventually. And when that happens, you wind up with a quiescent black hole that just sits there. The Milky Way has a 4 million solar mass black hole at the middle of it doing cream of nothing. We do believe that eventually there's a gas cloud in the vicinity of the Milky Way's black hole. Eventually that's going to wind its way into the black hole. We're going to get a brief period of activity. It won't be a quasar or a true AGN because it's not going to be super bright. It's not enough gas. But that's pretty much what happens. After you get done feeding, your quasar turns off and your black hole just sits there for the rest of eternity unless something wanders into the event horizon.
But the same dust that comes in, there is a lot of dust that evaporates, right?
Well, the dust, as it gets close, will evaporate. Actually, it sublimates. It goes from solid to gas. And a lot of times that will get pushed out or funneled in regardless.
Well, where it goes?
Once it crosses the event horizon, it's gone. Point of no return. It spirals in, joins the singularity in the middle, given our current physical picture of the black hole, and never comes back out. It's lost to the universe, period.
So you're saying that the black hole is a cone, like a kind of cone shape, or is
No, it's a sphere. A black hole is a sphere.
It works like a
It
sphere.
has an event horizon that matches what's called the Schwarzschild radius. And so that's roughly 3 kilometers per solar mass. So the Milky Way black hole is a sphere with a radius of about 12 million kilometers, all directions from the middle of it.
If it wasn't a sphere, then how is it able to suck? I mean,
They don't suck. Black holes don't suck. This is a common myth thanks to movies. Black holes are, if you took the sun and you switched the sun out for a black hole in the middle, first off, how big would it be? What would the radius be? 3 kilometers. 3 kilometers. So you'd have a radius of 3 kilometers for the sun. It would be a black hole. We'd have no light, but we'd keep going around it like nothing changed. As long as you don't change the mass. That's the key. If the mass is the same, you just keep going around it. Or if you slow down for some reason, you start working your way in. Now I'm going to spiral in and move across the event horizon and be lost. Black holes don't suck. If you take nothing away from my lecture today, that's a good one.
those weather hazards get and pointing north. How are the wind related to that?
Ah, good question. So it's actually our competitor. We don't like jets.
Jay, could you repeat the question for the online one?
So the question is a lot of times quasars have jets, polar jets that point vertical and down. So here's the accretion disk, and they point perpendicular to the disk. Jets are another way to take energy and gas out of the system and away from the black hole. And so we see them about the same fraction of time we see FeLoBALs or out for big winds, but they're not always in the same kind of object. Sometimes you have winds and you don't have jets. Sometimes you have jets and you don't have winds, and sometimes you have both. So they're not directly tied to one another. The question is which one's more efficient? So if I want to remove a lot of mass, the winds have a ton of mass, and they have a lot of gas that they're carrying with them. So it's a great way to remove mass, but they're moving only a few thousand kilometers per second. I say a few thousand like it's small change. But jet comparatively, are ultra-relativistic. They're moving at 99% of the speed of light, but they carry virtually no mass. So it's a great way to remove energy without removing mass. And then the winds are a great way to remove mass without removing a ton of energy. So it's kind of a balance, and there's a lot of people debating about which way is the best way to get rid of the material and energy.
But what else there could be jet?
What causes there to be jets?
Magnetic field?
It's a magnetic field thing. So my astronomy students all know the joke. Magnetic field, oh, I'm going to wave my hands and just magnetic field sweeping around the table. There are really, really good modelers that can describe jets, and they still only come close. Nobody has a perfect picture on how to make a ultra-relativistic jet from a quasar. Not perfectly, at least. They got decent pictures, but there's always something that's not quite right. So nobody has a great answer for that. Fire away.
I have not heard you mention,
Okay.
which is surprising to me, is gamma burst.
Gamma ray burst.
Yes.
So the statement is he's not heard me talk about gamma ray burst.
So what's the difference between gamma ray burst and jet?
So gamma ray bursts, there are two kinds of gamma ray bursts. Gamma ray bursts have two different models, one of which is you take, say, two neutron stars or two black holes, and you have them in orbit. Now, when you have two compact objects in a close orbit, they actually emit something called gravity waves. And so that will cause the orbit to decay because I'm taking energy out of them. If I take energy out, they're going to get closer and closer and closer until they finally merge. And when they do, there's a tremendous explosion. And a lot of times you can, since I've got angular momentum, it's going to make jets. If I happen to be looking down one of those jets, I see a gamma ray burst. Right? That's one way you can do it. The other hypothetical way to do it is to have what's called a hypernova. I'm not a huge fan of this idea, but you have a supermassive star, 120 solar masses. You know, big stars are like, 10. This is 120. So you have 120 solar masses, that goes supernova. They sometimes refer to it as a hypernova, and a lot of times we think there might be jets associated with that, which could also generate gamma radiation. The ones that come from quasars typically emit a lot of radio emission. Now you can also, if you're looking down the pipe of the jet, you can see what's called a blazar. So it's another nickname for quasars. And so those actually push a ton of light in our direction to hit all wavelengths, optical, X-ray, gamma, everything. And you just see the jet, you see nothing else. And so that's one way that we can look at that, but it won't give a ton of gamma ray emission. That's more like the other two phenomena that I referred to. Any other questions? All right. I want to give a hand to my two students. And thank you for hosting us.
Well, thanks for suggesting.
And thank you for coming.
I hope there'll be many more occasions like this.
I got two more in the waiting that, maybe next year-ish.
I'm not going to forget you. Cool. Yeah, let me stop the recording. Oh, it's actually working.
I guess I should have took questions from the
Oh, there
chat.
weren't any.